Hi everybody, this is an introduction to the laboratory for the week of October 5 for the Science 121 class here at Luther College, our general astronomy class. So this week in lab we will be doing parts of two exercises out of your lab book, Contemporary Activities in Astronomy by Hoff and Wilkerson, yours truly. So the first thing I'm going to talk to you about, you can do the exercise 5 activity or the exercise 3 activity first. You can mix them up a little bit as you want to work on them. I don't really care. I'm going to talk about the exercise 5 activity first from pages 55 and 56 in your lab book, where you're making an angle measuring device. So you're going to make a simple strip to measure angles. And the theory here of what we're trying to accomplish is to say we're going to use the idea that if we call the extent of something or the separation of two objects. So imagine this is a tree. You'll go outside and measure a tree here a little bit. And if you imagine this is a tree, that could be the height of the tree. Or you can think about it as the separation of the top of the tree and the bottom of the tree. And that way when you think about, oh, I want to go outside later as I'm doing project 1 and I want to measure the separation of two stars, that could be star 1 and star 2. Or the distance between the horizon and star 1, for example. So now you can go out and think about this as either the separation of two objects or the size of one object, which is the separation of the two ends or sides of that object. We're going to call that S. And we're going to call that S throughout the course, and we're going to use it quite a bit. So you want to get used to that idea. And we're going to call this distance R. And that angle right there as theta. So the angle, not half of that. Let's be careful about that. That's theta, and R is that total distance out here. Let's draw it that way. So theta is the full angle right there, and often we'll write S equals R theta, or theta equals S over R. And theta equals S over R. This works if that angle is in radians. Okay, and we're hoping that angle's not too big. We might run into problems doing that if this angle is too big, and we're going to work on that in lab. I'm going to have you measure some. What we're going to do is have you measure the size, the height of someone in your class, and try it from different distances away, and see how close you get to that person's actual height, and to see if there's a trend in how much you miss. And we'll talk about that. So that's one of the things that we want to do right here. Now, we don't often work in radians. It's not a unit that human beings use as much as, say, degrees. So we remember we talked in class the other day about 360 degrees, full circle, 180 degrees, a straight line, and so on. So if we want this to be in degrees, as your lab book will tell you, it's really theta is equal to 57 S over R in degrees. And the way we got that 57 is we took 360 degrees and divided it by the number of radians in a full circle, which is 2 pi. So we can do that calculation here and get a few more digits if we want to. We can say 360.0 degrees, that gives us 4 digits, divided by 2 pi. So that's divided by 2. And divide by pi, 3.14159. We won't lack for digits there, and that comes out to be 57.30. So if you really want this to be a little more precise, you can call that 57.30 S over R in degrees. Good. So that's the idea. Of how we're going to measure angles and what we're going to look at and how you're going to be measuring angles today in lab and how you're going to be measuring angles in the first project and how you're going to be measuring angles in the second project. So you're going to make an angle measuring strip to do this. And to make an angle measuring strip, you're going to make one you can take with you and carry around. This is yours. You want to keep it. Try not to lose it because you're going to use it today. You're going to use it in lab one other time, and you're going to use it for the first 2 projects. So this is something you want to carry with you. You're going to take a strip of plastic. So there's a strip of plastic. There's one on your table ready to go. And we'll have we'll have lines drawn on the board of known space between those lines. And with the known space between those lines, that space is going to be S. You're going to measure your distance away from those lines, and that's going to be R. And then you're going to want theta to be 5 degrees. So if you make theta 5 degrees, you can, once you know what S is, and you want theta to be 5 degrees, you can solve this equation for what distance you need to be away from those lines on the board. Then you step back, and as you step back, you hold this up and hold the position between those two lines. Mark them with your thumbs, and you can either have somebody help you, or you can come back to your desk and you can use your marker to draw where those lines are. Now, the trick to this is you want to be able to hold this out at arm's length and do it naturally, so you repeat. Because if this distance changes, then that angle is going to change. So you want to just be able to, whatever's comfortable and natural, just throw your arms up, and whatever that is, that's how you want to do this work. This way, or this way, or this way. You want to do this work and hold this thing up so you can see the again and again you get repeatability. I test the repeatability. Draw your lines and see how close your lines match to the lines on the board once you've made the strip. And so this is this is going to be your angle measuring strip to do this. And once you have this in 5 degree increments, you can go in with a ruler and subdivide this. You can take your ruler and measure the distance between those lines that you've drawn and subdivide those lines into 1 degree lines. So you can take your 5 degree lines and make them 1 degree lines by 1/5 of the space in there is going to be your degree. And then you can replicate that and get another 5 degrees and another 5 degrees and another 5 degrees, so that when you're done, your strip ought to look something like this. You know, there's a 5 degree line, there's a 5 degree line, there's a 5 degree line, and there's your 1, 2, 3, and 4 degree lines. 1, 2, 3, 4, 1, 2, 3, 4. So that's 10 degrees, 15 degrees. So you have 5 degree steps across there. And then when you've done that, what I would like for you to do is I would like for you to go outside. Hopefully it's going to be a nice week, it looks like, so enjoy a little bit of sunshine and a little bit of air, and go outside with your lab partners and measure the height of one another at different distances. So the height of the person, when you use your angle measuring device, the height of the person is going to be S, and the distance you are away from the person is R. And use your angle measuring device to get theta. So now you're going to determine S. You're going to say, oh, S is equal to R. S is equal to R theta divided by 57.3. Okay, so you measure the angle theta in degrees with your strip, and you divide it by 57.3. You multiply by your distance, and that's S. So then I'd like you to create a table to say this is your distance R, and this is, you really only need 2 columns in the table. This is your measured height, your measured S value. So if that's your measured height, I want to see how that height, how consistent, this is one of the things we have to do to test our data again and again and again, is to say, how consistent is that height from measurement to measurement, and is there a trend? Is there a bias that shows that the height is trending towards some value as R gets further and further and further and further away, so that it looks like you have some built-in error, some built-in bias as you get closer and closer and closer, or further and further and further. And we have to start at, or is it just random noise around, and how much is that random noise around? Now, you should be able to measure the person's height, and so you know the known height. It's not really known, it's just measured in a different way. So use your meter stick to measure the height of the person, and so you have the known height. So let's make a 3rd column out here. Let's take the measured height divided by the measured height by angle. That's what you have in this column, divided by the measured height by meter stick. if we take the meter stick to be a precise way, a relatively accurate way, and a relatively precise way of measuring the person's height, then if the angle method is also both accurate and precise, then that ratio should be 1 all the way down through there. If that's not 1, is it trending toward or away from 1 as R grows? And how much is it jumping around 1? How much it jumps around is related to the precision of the measurement. If this measurement's hard for us to do, then you're gonna have a lot of different you're gonna have variation every time you do this. You're gonna see this thing bouncing around a lot. If there is a built-in error or a built-in bias in this measuring device that we made, or in the approach that we're taking to do this measurement, then it's going to be above 1 or below 1 and consistently there. It could be very precise and not jump around at all, but it can miss 1. And that means it's not very accurate. Again, presuming that the meter stick method is accurate. We haven't tested that to show that that's accurate. There's all of these things. When we make measurements of the physical universe, all of these things go into it, and we have to be really careful about how we're going about understanding our measurements. So this is what I'd like for you to do. Throw in one more measurement when you're outside. Pick a tree or a light pole and try to measure the height of that tree or light pole and report it. So report a tree / light pole, something like that, with whatever distance you think is good. You can do a little quick testing of your data to see if you like further distances away or closer distances to do this, and decide accordingly. And you can pick that could be a building. Pick Maine. If you want to pick Maine and figure out how tall Maine is, do that. You can do it from all the way over here at Valders. And think about what kind of things: unevenness of the ground, angle of the ground, elevation of the ground. What kind of things might be leading to errors and biases in these measurements of the trees? If I remember all the way back in high school, which was a long time ago, I took a class that included a forestry unit, and they talked about measuring the board feet in a tree. You go outside, we practiced going outside, measuring how many board feet of lumber there was in a tree, and we held a stick up and we paced back the distance from the tree and made a measurement, and the stick told us how many board feet of lumber. And they called it a Biltmore stick, if I remember that correctly, all those years ago. But that's what we got right here. This is what you're doing. This is what you're using right now, as you're basically building what these foresters in my high school class would have called a Biltmore stick, if I remember that name correctly all these years ago. So when you're done, so cut to one more idea. One more idea is to say, when you measure this R, either outside or in the lab, you can either measure the R with your meter stick or your 2-meter stick or your tape reel every single time, or you can count paces. If you think your paces are consistent, just pace off 10 paces or 20 paces and measure that with your reel or your meter stick or whatever, and then you can have a 1 pace equals X meters, and then you can use that and just do pacing off as you're outside and doing these measurements, and you don't have to measure with your tape every single time. So that's one thing. When you write this lab up, basically what I want you to do is I want you to turn something into me that's this table, and then I want 1 paragraph of discussion of that table to talk about the things we talked about here. What do you see? Talk about the accuracy and the precision of your measurements as we talked about here. Talk about whether it looks like your measurements are trending one direction or another as you get further away from the person. Talk about the kinds of problems that might be built into measuring the building height or the tree height or the light pole height as we talk about this, and tell me what you measured right there. So give me the table, give me a paragraph description of what it is that you've seen in the trends in this data, and help us understand the uncertainty of this data, what is going to be a problem as we try to use this measuring in the sky later on. So that's the first part of the lab. I'm going to stop this right here, and I'll talk to you about the other part of the lab in just a moment.